Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. Previously, we've looked at circuits that turn voltages to currents according to a linear relationship. This lecture will involve looking at similar circuits that apply an exponential relationship. Now, I've mentioned these previously in the context of voltage-controlled oscillators. The circuits I presented in those lectures were really current-controlled oscillators, and I hand-waved a bit and said later we'll look at a circuit to create the currents for these oscillators. But circuits with these exponential properties are useful beyond voltage-controlled oscillators. They're also useful for controlling voltage-controlled amplifiers and voltage-controlled filters, because a lot of audio qualities, in particular volume and especially pitch, are perceived on a logarithmic scale by human beings. Our primary tool in our quest is going to be the humble bipolar junction transistor. As is usual, I'm going to assume that the current flowing through the base is negligible. Now, there is a current flowing through the base. By the way BJTs operate, there has to be a current, but I'm going to assume it's really small, so I'll assume that the current flowing out of the emitter is the same as flowing into the collector of this NPN transistor. We're going to use a model for transistor behavior that looks at the difference of voltages between the base and the emitter, which I'll call VBE, and everybody else calls it VBE2, and it tells us the collector current as a function of that base to emitter voltage, this thing called the thermal voltage that we've previously seen in the context of operational transconductance amplifiers, and we usually assume that's something like 25 or 26 millivolts at room temperature, which we'll assume is 25 degrees Celsius or 298 degrees Kelvin. That Kelvin business is going to become important later. And here we're not going to do any sort of small signal linearizations. We're using this transistor in its full exponential glory. So this exponent is multiplied by this constant called IS. And as we'll see in a second, that's something of a misnomer because that's a highly variable constant. So we're going to assume that we can ignore the -1 part here, but that's legitimate if this current flowing into the collector is a good portion larger than the saturation current. So here I'm generally using lowercase letters to represent things that we, the user, are changing, and capital letters to indicate either things that we, the user, are trying to fix or have been given to us by the physics of the particular transistor. Now, the BJT changes its characteristics a lot with temperature, which presents a lot of challenges. One of the challenges is that VT itself changes with temperature, as you might expect, because it's called a thermovoltage. This isn't really something that we've directly addressed so far. Now, that VT is given by K, which is Boltzmann constant, times the temperature in Kelvin, divided by the charge of the electron. And again, we've usually assumed this to be 25 to 26 millivolts. And for something like a voltage-controlled amplifier, you probably wouldn't worry about this variation too much. But there's actually a much worse variation, which is that IS itself changes drastically with temperature. A general rule of thumb is that people will say it will double for every 10 degrees Kelvin. Now, if you're building a voltage-controlled amplifier, maybe that's not a huge deal, but for something like a voltage-controlled filter or a voltage-controlled oscillator, you definitely want to deal with that. And in case you're curious, voltage-controlled filters are what we're going to be talking about for the next lecture and throughout the entire rest of the course. And as expected, most of these voltage-controlled filter circuits I'll show you are really current-controlled filters, and it's up to you to put a voltage-to-current converter as part of the control input. Now, as far as the thermal voltage is concerned, you may or may not bother with dealing with that for a voltage-controlled filter, but you'll definitely have to deal with both of these if you're dealing with a voltage-controlled oscillator, because humans are exquisitely sensitive to variations in frequency, and you don't have to have a lot of musical talent or training to pick up on that. Everybody's going to hear it. So the trick we're going to use is to use a pair of transistors. So we may not know what their characteristics are, but we're going to suppose that their characteristics are the same. Ideally, these are built on the same die, so there are two transistors right next to each other, and they're going to be thermally coupled so that their characteristics will change in tandem with temperature. If you're using discrete transistors that you've gone through a matching process for, like they used to do at places like Moog Music a long time ago, you'd want to put these close together on the PCB and sandwich them with some thermal compound to make sure they stay at the same temperature. This is a pretty standard trick in analog circuit design, particularly for analog integrated circuit design. Basically, the entire die on the chip defaults to one giant transistor unless you want to split it up and do otherwise, which of course you want to do. But basically, the transistors are pretty cheap on a chip, so you might as well use them. And using matched sets of transistors where you don't know the characteristic of any one transistor, but you know that they're going to have similar characteristics is a thing that you can exploit in your design. So what I'm going to do here is write the collector currents over each other, so I'm going to divide them. Now, this is just for doing some math to get a sense of what's going on. I'm not actually building a divider anywhere in this circuit. So if I divide the two collector currents, just substituting in the expressions we had on the previous slide, the beautiful thing that you'll see about this, of course, is that the IS's cancel. So that saturation current, which is the main thing that heavily varies with temperature, goes away. So I can take IC1, move it up to the numerator on the other side by just multiplying both sides by IC1. And I can combine the exponents by realizing something like e to the a over e to the b is e to the a minus b, just by the algebraic properties of exponents. So now I have the difference of the base emitter voltages. But if I write this out explicitly, I see that the emitter voltages wind up canceling. I have plus VE from the second term, and then I'll have minus VE from the first term. So those go away. And what I really have is the difference between the bases. Now, this is not a particularly novel calculation. This is the sort of calculation you do if you want to study operational transconductance amplifiers made with BJTs. This is also just the basic of a differential amplifier pair that pretty much shows up in any analog circuits class. It's the front end of every op-amp that has BJT inputs. And if you're using MOSFETs or JFETs, well, it's the same kind of structure, just with MOSFETs or JFETs. So lots of kinds of circuits have this kind of structure at their input. What's particular about synthesizers here is the way we're going to use this pair. That's actually a current sink. So for instance, in the sawtooth and triangle wave oscillators we've looked at so far, we've been pulling current out of a capacitor in the feedback loop of an op-amp. Of course, there's other kinds of oscillator designs that have the capacitor just kind of floating and not in the feedback loop of an op-amp. But whatever you're doing, the same idea applies. So this current sink here is connected to the kinds of circuits I've shown you previously in the triangle and sawtooth VCO lectures. So to facilitate this, I want to fix a reference current, I'll call IREF, and pump that into this collector of this BJT. And if I do that, well, my IC1, that's my reference current, and now I'm starting to actually build my converter. So I want to turn a voltage into a current. There's times where you might want to use both of these inputs. You might want to have a differential voltage input. But here it's perfectly fine to just ground, say, B2, and that will give me this exponential relationship in terms of an input voltage at the base and this IREF that we pick. Now, this is a little unsatisfying because we have a minus sign here, and we really want something that grows the current exponentially as the voltage increases, but we'll deal with that in the next slide, and you'll see why we set it up this way with the minus sign at this stage. So to fix the reference current, let's take a voltage. I'm going to call this HR for high reference. You can take this out of a voltage regulator if you wanted to build a pretty precise VCO. Quite often I see people just tying this to whatever the positive supply rail is. And that voltage is connected to RF, our reference resistor, to create our reference current. Now, the problem with this is that the voltage at this node, the way I've drawn it, will float around a bit. It will be nice if I could fix the voltage at the collector. Well, the next thing to think about there is it would be nice if I could decide on a voltage somewhere in the circuit and then clone that voltage and have it show up there. Because then I would be in control of what IREF is, and then I could change IFreq by just changing the voltage at the base. Well, when I say things like, if we could clone a voltage, you should imagine at this point that I'm going to pull out an op amp. So here we've put an op amp, and this is a little weirder than what you might have seen before. Don't let the fact that there's something coming into the base here throw you. I have a transistor in the feedback loop of an op amp, and the negative feedback characteristics of this structure will cause the output of the op amp to try to produce whatever voltage and current is necessary to hold the negative terminal at a voltage of VLR, and the LR here stands for the low reference. Now in the circuit I'm going to show you later, which is the Howe Chamberlain Musical Applications and Microprocessors Design from Electronotes, this is grounded, so VLR is ground. In the Buchla designs I've seen, if I recall correctly, he usually holds this at around 0.7 volts above ground. But whatever it is, our ability to fix that voltage there means that we can figure out what IREF is. It's just the difference between those voltages divided by RF. So that's kind of nice. But there's a few things that are still unsatisfying. One is I have this minus sign here. The other is that small changes in the voltage here are going to give me some pretty big changes in the current. I might want to be able to control it with a wider voltage range that I get to pick. So let's deal with both of these problems at once by sticking an inverting op-amp configuration in front. The fact that this is an inverting op-amp will give me the minus sign that I need, and I can change R1 and RF in order to scale that input voltage so that a nice relationship of voltages presented at the user maps to something that the transistor understands. So, usually I would call the gain of this circuit minus RF over R1. I'm going to define this scaling factor with this little hat here, and you'll see a little later why I'm putting the hat on it and just not using this funky looking S. Now, I think it makes the most sense to characterize the use of this op amp in terms of this S being a positive number. So RF over R1 is really the absolute value of the gain of this inverting configuration. So now when I throw that S hat in, by the fact that this is an inverting configuration, I can take this minus sign and flip it to a plus sign. And here I'm explicitly writing out the plus sign just so people don't think that I forgot the minus sign. Now, I'm using the hat on the S to indicate this RF over R1, the particular gain that I get going through this op amp. In the next slide, I've taken the hat off the S because I want to approach that scaling factor from a different angle and find out ideally what total scaling factor would I need in order to have a certain number of volts correspond to a change in octave. So here's the general idea. Here's the formula with the exponent we've been looking at for a while now. Let's imagine that I want to add some change to that voltage. I'm going to add a delta Vn to Vn, and I'm going to ask the question, well, for some delta Vn, I want to figure out what gives me a 2 out. Well, in particular, what I probably want to do is to specify a volts per octave ahead of time. So I'll fix this delta, and then I'm going to try to figure out what the scaling factor I need is in order to get that doubling of frequency, which corresponds to an octave change of pitch. If I take this expression here, the second one, and divide it by the first one, well, on the left, the ifreaks go away, and the irefs go away, those cancel. And then when I take this exponential here and divide it by this exponential here, using the algebraic properties of dealing with exponentials, these guys wind up canceling, and I'm left with just the scaling factor times my voltage change over the thermal voltage. So to solve for S, I would take the natural logarithm of both sides, and then I can multiply both sides by VT, which would stick the VT up here next to the natural logarithm of 2, and then to write this final equation, I just flip the order. All right, so plugging in some numbers here, let's suppose for a second we're operating at that room temperature that's 298 degrees Kelvin or 25 degrees Celsius, which I think is 77 degrees Fahrenheit, which is actually a bit warm for me. So let's take 26 millivolts here for VT. We'll deal with the change in temperature of the thermal voltage later on in the lecture. Right now we're just dealing with canceling out that saturation current, that I sub S. Okay, so logarithm of 2 is like 0.6931. And now we get to pick what volts per octave we want. Buchla systems use a 1.2 volt standard, and that's kind of nice because it corresponds to 100 millivolts per half step, which is the pitch distance between keys on the piano. But most other manufacturers use the Moog standard of 1 volt per octave, which is easier to remember as 1 volt per octave, and is kind of nice if you're using a voltage generator as a piece of test equipment that is digital and lets you change the first digit to the left of the decimal point by an increment or decrement of 1 each direction, because that corresponds to an octave. That's kind of fun. It's a bit more awkward in terms of half steps because you have something like 83 millivolts per half step instead of 100 millivolts per half step, like with the Buchla standard. But this is the most common one, so we'll go with it. Anyway, multiplying all this out, I get a scale factor of 0.018. So put a pin in that, 0.018. And it's also useful to view this as a fraction, which I'll write as 1 over 55.5. Keep that in your head as well. Now, people tend not to take the output of the op-amp and slam it right into the base of the transistor. Usually they will use a small value resistor here and an even smaller value trim pot to be able to adjust that volts per octave precisely. Now, there's other variations. I've seen variations where they put a small trim pot in the feedback loop in series with a much larger resistor. So different designers handle this different ways. Here's the particular example corresponding to the VCO circuit and the musical applications of microprocessors that we've looked at previously. Hal cites Electronotes as the original source for this design, and the fact that they're using a 301 op-amp here suggests to me that this is a pretty old design, even if I didn't know anything else about the circuit. One thing I would particularly like to highlight is the capacitor that's sort of here in a local feedback loop of the op-amp. This capacitor is here for stability. I left it out on the previous slides at an attempt for clarity, but I would like to point out I've always seen this capacitor in every variation of the circuit I've ever seen. They never just leave this blank. But I want to be clear that this is for stability. It doesn't really have a musical effect. And in particular, don't get this mixed up with the integration capacitor that's part of the sawtooth or the triangle core. So, notice that he has a 1 mega ohm resistance here. That's pretty big. He uses a 10 volt source for his reference to create the reference current. That's lower than the much wider voltage range that he's using to, say, power the op amps off of. So he's generating this using some sort of regulator somewhere. Now, take that 10 volts, divide it by 1,000,000 ohms. That's 10 microamps. So IREF is not that big. But remember, we're multiplying that by a function that's exponential in voltage. So in terms of what's happening in the input circuitry, I've described it as the total scale going through both the op-amp and this simple passive divider here as being S hat times S tilde, where I'm using S hat to represent the change that we're getting from the op-amp circuit, and I'm using S tilde to represent the attenuation that we're getting through this passive voltage divider. Notice that this 2K over 100K, by itself, it's 1 over 50, whereas previously I showed you that if we wanted to do all of the change just with the op-amp without this extra bit added on to the output of the op-amp, we would want this to be something like 1 over 55. Okay, so what is the attenuator doing? Well, I have a voltage divider. The total resistance in the denominator is going to be 390 plus 100, which gives me that 490 ohms. And let's suppose for a second that we set this trim pot to the middle, so it's taking that 100 ohms and splitting it between 50 ohms and 50 ohms, assuming it's a linear pot. So the voltage is being divided over 390 ohms plus 50 ohms, which gives me this 440 ohms. Now, when I pile all of that together, I get that 0.018. If I just use this, I would get 0.02. But assuming we're setting this in the middle, that gives us that extra little drop of voltage that we need to get the scaling factor that we want. Now, of course, the reason we need the trim pot here is that we'll probably need to do some tweaks because this is a fairly sensitive circuit compared to most of what we look at in synthesizers. Okay, so we've seen how to use a pair of transistors to combat the way the saturation current isobest changes with temperature, and we've seen how to overall set a volts per octave parameter. Now we need to deal with VT, this so-called thermal voltage. The way we've presented it so far is that we implement the scaling factor according to this ratio of resistances in the input op-amp and according to this little tweak S tilde we get from that resistor divider with the trim pot. Now, VT isn't a constant. It changes with temperature. Something I want to remind you of repeatedly is that this temperature is in terms of kelvins, not Celsius and definitely not Fahrenheit. K is Boltzmann's constant. Q is the charge of an electron. Fortunately, we won't actually have to look up either of those parameters individually in this lecture. All right, so how can we deal with this? Well, I have a thing on the right that's changing with temperature. Maybe what I should do is have something on the left that also changes in temperature, but changes the same way. So let's use something called a Tempco resistor, temperature coefficient resistor. So here, instead of using a regular resistor in the feedback path of the op-amp, we're going to use one of these Tempcos. Tempcos are defined in terms of some reference temperature. Now, if the actual temperature T matches your reference temperature T0, then this term here is 0, and then we get what I call R sub O out. So this is sort of the baseline resistance of your Tempco resistor. And what describes how the resistance changes with temperature is this coefficient sitting here that I've just called coef. All resistors will change their resistance and their overall properties with temperature, but usually you don't want them to do that, and the people who are manufacturing the resistors try to make that variation as small as they can. And to the extent that they do vary, they tend to vary in a way that's fairly unpredictable. Tempco resistors are much more expensive than regular resistors because they've been carefully constructed to have these specific changes with temperature. If I were to take this expression for RF and plug it in on the left-hand side, I have something that looks like this. And now I'm going to do something that's fairly odd. I'm going to take this nice simple formula here and rewrite it in a more complicated way. Now, I haven't changed the formula. All I've done is taken a T0 and subtracted a T0 and then put in some parentheses. You'll see why I'm doing this in a second. Now, if you've watched or wind up watching some of my older credier lectures, you'll find that I generally describe this differently every time I teach the class. And I'll be honest, this temperature coefficient stuff always confuses me. So each time I teach the class, I do this calculation in a different, oddly roundabout way. And right now, this particular roundabout way is the way that sort of makes most sense to my brain to try to visualize what's going on. There's probably quicker ways to get from point A to point B. This is just what's fitting my brain at the moment. All right, so I'm mostly going to keep the stuff on the left the same for a while. The main thing I did on the right is that I took this term with the T0 here and separated it from this term with the T0 over here. And then in the next line, all I'm doing is taking this second term and multiplying the numerator and the denominator by T0. So I haven't changed anything on the left or in the first term on the right, and I'm just making these minor tweaks to what's on the right. Now, the reason I want to do that is I notice there's a K T0 over Q here, so I'd like to write a K T0 over Q here. And I'm hoping if we do this, we can avoid having to directly deal with K or directly deal with Q. Or for that matter, even directly deal with K over Q. So all I've done here is taken the last line on the previous slide and copied it to the top of this slide. Now what I'm going to do is I'm going to take the K T0 over Q and this K T0 over Q and just replace them both with V T0. Now this V T0 at that 298 degrees Kelvin, 25 degrees Celsius, 77 degrees Fahrenheit. That's basically what I've simply been calling VT through all of the previous lectures. Let me define an S0, which is sort of this ideal scaling factor, assuming that the actual temperature was T0. If I do that, then I can take this whole mess here, and then I can also take this whole mess here and rewrite those as S0. And now I can take the expression and collapse it down to something that looks a little nicer. So let me take that expression, copy it to the top of the next slide, and notice that I can match things up. This S0 here matches up with R0 over R1 S tilde. So here I have R0 over R1 S tilde. So that can correspond to an S naught that shows up here, incorporating all of these factors. So those match up. I have a T minus T naught that matches up with this T minus T naught. And if this S naught matches up with this R naught S tilde all divided by R1, then the coefficient must match up with 1 over T naught. Now, if I plug in our T naught of 298 degrees Kelvin, which most Tempcos have as their standard reference temperature, that gives us 0.0034. Now, Tempco resistors are spec'd in parts per million. So with percents, you move the decimal point over twice. With parts per million, you move it over 6 times. So I would go 1, 2, 3, 4, 5, 6. So that would give me a couple zeros here. And I would go out and buy a 2 kil Tempco. And the reason you would buy a 3300 parts per million Tempco instead of a 3400 parts per million Tempco is that these are things that are actually on the market and you can go buy them. But you would be hard-pressed to find a 3400 parts per million, and then you declare it close enough for rock and roll. Now, one thing you might have wondered back when I showed a slide like this is why did we put the voltage into here and put the ground here when that gave us a minus sign that we wound up having to use an op amp to provide an inversion operation to get rid of? Why didn't we ground what we had over here and put our input in over here? Well, inevitably, you're going to want to add up some control voltages in a nice way anyway. And the most convenient way to do that is with an op amp in this inverting configuration that gives you this nice mixing node here. So if you're going to have something that inverts anyway, you might as well put in something that will kind of invert it back. So over here, this VN, that would usually correspond to a volts per octave kind of source that's coming from an old school Moog 1960s controller keyboard where it's basically this big resistor chain. Or maybe it's coming out of a modern MIDI to CV converter that uses that 1 volt per octave standard or whatever your standard is. And quite often what you would do is you would put a few other things in here. You might put a potentiometer in front of one of these, and then you would have another input here. This might be something that you would have a low frequency oscillator to make either a siren kind of sound or a more subtle vibrato sound like a violin player or an opera singer might use. And you would use this pot to control how much that LFO influences the pitch. Or you might put an envelope generator here that puts a slight rise in pitch at the very start of the note. That happens with a lot of brass kind of instruments. And maybe what you would have here, maybe it wouldn't be 100K, maybe it would be 10K, maybe it would be 20K, whatever it is you're doing. You might have some front panel control. You might have some sort of resistor here and some sort of resistor here going to whatever your positive voltage supply is. Let's call it VCC just for fun. Down here you might have a VEE, something like plus 12 or minus 12 for Eurorack or plus 15, minus 15 for Buchla or MOTM. This would basically set a base pitch before you put any input into it. So even if you didn't plug in a keyboard or whatever, or plug in any other external source, you could still change the pitch by turning this knob. And this gives you a nice structure for mixing all of these control voltages together. Now, to give credit where it's due, we should go to schmitzbits.de, the website of Rene Schmitz. And he has a really amazing website here. He has all sorts of designs of all kinds of different oscillators and different envelopes, different VCA designs of all kinds of various sorts, all kinds of fun stuff, all kinds of filters, tons and tons of filters, various adaptations of filters. We'll actually look at some of these later in the class. And in particular, he has this great write-up on exponential converters and temperature compensation. So if anything that I have said in this lecture is confusing or wrong, that's on me. But if anything that you've heard me say is accurate and useful, thanks for that should go to Rene. The particular kinds of circuits he looks at here are a little bit different. The circuits we looked at had an op-amp here that did a pretty large drop down of the voltage, and then there is a set of resistors here that did a smaller bit of attenuation. Another approach is just to use the op-amp to do mixing, so your feedback resistors and your input resistors aren't that different, and you do most of the drop down here with a much larger resistor at the top part of this voltage divider, and then you put the Tempco here. Now, of course, if you wanted to be super technical about it, the math of this divider would be different. It's not just feedback resistance over input resistance the way we had with the op-amp circuit. With the divider, you get the full range, including the Tempco in the denominator, but you can usually reasonably approximate it and adapt the kind of formulas we did in lecture. Anyway, I would highly recommend that you read this website. Now, once you've mastered the material on Renee's website, you should go check out the website of Ian Fritz. Ian is one of the most technically sophisticated designers in the synth do-it-yourself scene, and he has a bunch of amazing stuff for you to learn from. If we click on his synth stuff and scroll down a bit, there's really astonishingly original and well-designed circuits in here, and he also has a great write-up about temperature compensation that goes into a lot more detail, and much of this is well beyond what I've dug into myself. To be clear, a lot of these designers are admittedly much more qualified to teach this class than I am. I just happen to luck out and be a professor at the university, so I get to do this. And to a large extent, what I'm presenting in these lectures is really the things that I've learned from the Synth Do-It-Yourself mailing list, from people like Ian and from people like Renee. And I've taken at least the top level of some of those most interesting things and tried to order it into a coherent presentation. So if you are finding these lectures useful, I would highly recommend to go find these original sources and dig in.